All right, so I will try to provide you a little bit highlights on the electromagnetics because there are some gap. Before I left, there are actually a lot of improvements on the electromagnetic simulations. So this is something I would like to highlight to you a little bit. Yeah. So on the left-hand side, this is actually how simulations is carried out in big commercial customers, for instance. In commercial customers, normally you have a designer where they are focusing on drawing the CAD designs. Okay. And then normally they'll pass this CAD design to simulation engineer. Or they will pass it to data analyst, okay, to run further analysis. Okay, but the problem is the process over here and over here they might need to change the structures in order to fulfill the the specifications they set earlier. Okay, so you might see they are exchanging the data through the email. Most of the time, your mailbox is bombarded with a big file size. Okay, but then, I would say this type of methods is actually very time consuming, as in, you need to send data from here to there. And then sometimes, the file size is too big, then you need to use a thumb drive to send the information. So maybe you need to upload to a cloud. And then, somebody who needs it, then they will go and download all this data. So over here, you can see there might be some potential problem, as everyone is not using the same versions of the CAD file. But then if we try to look at the modern way of managing the data, you can see on the right hand side, we actually switch everything to platform. We call it 3D experience platform. So in a 3D experience platform, all this guy will be use the software through this particular platform. Okay, so designer, it's the same thing. They are drawing the CAD file, and then when they are done with the designs of the CAD, then they will actually save it in the cloud. So whoever needs to run simulations, they'll directly go to the cloud and then try to download the data and then try to run the simulations. And the good thing about it is, when you are trying to perform the parameter sweep, for instance, you are changing the parameters. So all these parameters will be changed automatically and instantly inside this cloud as well. So whoever needs to access the data at the later stage, be sure that they are actually accessing to the latest information. So this is actually very efficient. You don't have to use the email to transfer the data. You don't have to worry about the different versions you are working on. And eventually you actually save a lot of management time, I would say. Okay, so this is what we call as a ModSim concept. ModSim is actually the short form of modeling simulations. Okay, so modeling means somebody who is drawing the CAD, and then simulation is someone who is using the CAD file to run the respective simulations. For instance, you have electromagnetic simulations, you have the structure simulations. Okay, so this is actually the parts where we were focusing just now. But of course, we can do more. We can actually do the test management. We can actually do the product management. For instance, you have colleagues from QE departments. They would like to check the performance of this. So they normally will require the simulation engineer to run a few tests to validate their designs. So they can just specify all the requirements here, and then the guys in the ModSim side, they see the requirement, they will run the test, and then they'll provide the results. So that actually gives a complete flow on how do we develop a new product. Okay, so that is actually something that is more ahead. So in case you're interested with the ModSim, you can actually talk to Sigma Solutions. I think besides electromagnetic simulations, we can actually offer more. We offer even ModSim level, and just a little bit additional words on the AI. So you can see every company is developing on the AI. Okay, so for Dassault it's the same as well, and then our definitions to have this AI is we will actually try to integrate this ModSim as well. So means you will need to have the CAD data, and then we combine together with the simulations, and then we add in the AI ML elements inside there. Then they will actually give us the complete AI solutions for the customers. All right. So this is the agenda where I'm going to talk about. So we already spoke about this ModSim, and the rest will be more on the feature sides. So I chose these features simply because I think these are something very interesting, where some people, they are not aware of what we are offering from time to time. So perhaps, you have a very good understanding on our electromagnetic simulations, but probably that will be the conventional ones. So let's look at, what are the good highlights where you might want to integrate this into your design workflow in the future. Okay, first one is the TLM solver, and the second one is DDM. DDM is actually the frequency domain solver. And then there's the last one, which is the non-parametric optimizations. This is something very simple. It actually open up a new domain to design some engineering parts or components. All right, so let's look at the first one, TLM solver. So TLM solver is nothing but just our transient solver. So I'm not sure whether you are aware of, but in our transient solver, we actually have two types. The first one, we call it FIT, which is the conventional ones where, it comes together with CST. And then besides that, we actually have this TLM solver, transmission line matrix. So this is, offering a little bit extra on what we can do with the frequency domain, finite integration solver. Okay, so, normally transient solver is used to simulate very complicated structures. Mobile phone like this. If you want to use a frequency domain solver to solve it, then perhaps you'll run into problems like, insufficient memory. Okay, so when we are using transient solver, normally we use it to simulate very complicated structures. For instance, look at these mobile phones. We actually have a lot of antennas inside, right? So look at the number of cells. Is a lot. Okay. So with the conventional FIT, you can see that the mesh is going to look like this. Okay. But then when we switch to TLM, it's going to look like this. So it's still the same hexahedral mesh, but I think over here you can see this area. We actually try to simplify the mesh. So this is what we are doing over here. For instance, at the area, which is not critical, for instance, here is filled up with a lot of air. So we try to combine all the cells together so that we are able to create a cell lumping effect, which is eventually bringing the number of mesh very little. That means reduce the number of mesh. Okay, and of course, with this TLM solver, we have the PBA, the famous technique we use in the time domain solver. So means, with this, we are able to get a very good accuracy on the simulation results. Okay, so these are the other example. For instance, we have this millimeter wave antenna. So this is how we mesh it with the FIT. But then when it comes to the TLM solver, you can see, we try to do some cell lumping. So we will remain the dense mesh at the important area, but then at the area which is far away from the antenna, we know the changes of the field is going to be very little. So that's why, we try to combine them together. That will actually give us a very good efficiency, as in, there's a huge reductions in the mesh count, 99%. So imagine, you have 1 billion mesh cells. So end up you are going to have, 10 million mesh cells. 1 million mesh cells. So that's a big reductions, and that will actually speed up your entire simulations. Okay, so this is some comparisons on the results. You can see this is the S parameter, this is the far field results. They are more or less the same. So it means that TLM is actually suitable to use in these type of applications. Okay, so this is a summary. So we are introducing you new dimensions to simulate complicated structures. It could offer you better efficiency with the same setup. And then I think in the modern electronics, I would say that TLM solver is actually quite suitable to be used. All right, so let's go to the next topic, which is the domain decomposition solver. Now, this is actually our frequency solver. But they actually add some extra techniques to make it more efficient. So how this thing works is, for instance, in the big structures, you can actually add, you can try to actually cut it into smaller parts, like what you are seeing here. So this is actually the entire model. And then what we do is we try to cut it into a smaller piece. And then for smaller piece, we will actually use the individual core inside your CPU to solve it. So with that, they're actually able to achieve a better efficiency. Okay, so the bottleneck of the frequency domain solver is, when the mesh required is increasing, then it actually you actually need to have a more RAM, yeah, to solve that kind of problem. So it's actually a non-linear kind of relationship. So what we try to do is we try to keep the mesh cells small so that the number of mesh cells in these cells is small, so that you are able to operate in the linear region. So then with that, it is actually able to have a very good efficiency in solving those problems. Okay, so when we are talking about this DTM, yeah, we actually see several enhancements. For instance, we try to use this in the let's say base station antenna. We try to use it in PC boards. We are actually able to see a speed up. At least when some people they are trying to use a frequency domain solver, yeah, they are not able to solve the problems because they are heading into the insufficient memory problems. Okay, but then with this DDM, yeah, we are actually able to solve these kind of problems. Okay, but of course you are not targeting to have a very big, super large structures because still you will still have the memory issues. But then we are talking about the reasonable ones. So let's look at what are the examples we are working on. So let's say now you have a base station antenna. This base station antenna, you actually have the repeating elements. For instance, in this case, you actually have the low frequency element, which is on the top. Then you have a high frequency element, which is at the bottom. You can see that, we can actually utilize this DTM method. And then in the end, when we are trying to compare the version alone, 2025, 2026, you can see, for these structures, we actually require lesser memory to solve them. Yeah. So when we are running any problems with the frequency domain solver, bear in mind that you need to have a lot of RAM. Yeah. You cannot expect yourself to run with only 64 gigabyte of RAM, but then you want to solve such a complicated problem. It doesn't really work. All right, so I am giving you more example as well. As you can see here, you have this complicated base station antenna. It has a radome as well. So as usual, they have these low frequency elements and high frequency elements, and we are trying to simulate from 1.6 to 3 gigahertz. Okay, so as usual, we normally just use one adaptive frequency point. And the funny thing or the special thing about this particular structures is it has a lot of elements. Yeah, so it has 56 ports. So in this case, sometimes our frequency domain can be more efficient compared to transient solver. So the reason being is in transient solver, you need to run port by port. But if you try to switch to frequency domain solver, you can actually solve all the ports at the same time simultaneously. So means if let's say everything fits, like the mesh can fit into the required RAM, I mean the available RAM in the computer, then we would say this is actually much more efficient. So look at this. We have 7.8 milli mesh that cell, and then we just need to have 4 hours 57 minutes to solve this. Of course, we try to limit the number of samples. Okay, so this is already good enough for us to look at the S parameters, and it should give you the desired frequency response in terms of far field, E field, or whatever as well. Okay, so this is the example number 2. You can see the complexity definitely is there as well. Yeah, and you can see the number of mesh cells is 2.38, is relatively smaller compared to the previous one. And then you see we are just, we just need 2 hours to complete the simulations. So this is another one. So you can see the number of mesh cells is 111 million mesh cells. So before that, something like this, it can only be simulated with the transient solver. But then with the DDM, it is still possible to simulate this, but we actually need some MPI nodes. We need 4 computers at the same time. We combine them together. And we just need 11 hours to get the simulation done. All right. So I'm coming to the last part of what I would like to share with you. This is about the non-parametric optimizations. Okay, let's look at what is non-parametric optimizations. Okay, so the conventional ones we call it parameterized optimizations, and the ones where I'm going to introduce to you is called non-parametric optimizations. Parametric optimizations is nothing but when you want to run the structures, you need to have the structures equipped with the parameters. Okay, for instance, like this. Okay, and so in CST itself, we do have this optimizer. We have several types of optimizations strategies, and we have to choose one of them. And then after that, with the parameters you have in the simulation model, you need to tell them, how am I going to vary this? So what's the range from the min to max? Okay, but then when we come to the non-parametric optimizations, I think the main difference is the structures where we want them to change doesn't need to equip with any parameters. Okay, so it looks like this. Okay, so look at, before optimization it looks like this, then after the optimization it looks like this. So you can see, there are some corner here, they are actually dented. Yeah, they are going intruded inside. Okay, but then when we come to the optimization goal, is actually the same. Yeah, so means, when you are running the optimizations, the first thing is you need to tell them what you want to change. Yeah, whether it's equipped with the parameters on the parameterized optimizations, or when we are going to the non-parameterized optimizations, we just need to tell them. So where is your design space, which is this one in this case. Okay, and the second one is we need to tell them what's our goal. I mean, we change so many things, I think, for only one purpose. Yeah, we want to satisfy our design goal. All right, so let's look at, what is inside these non-parametric optimizations. So in fact, this is the technique which is widely used in the structure simulations. But then, after CST was acquired by Simulia or Dassault as a whole, okay, and then we found out Tosca is actually the tool that can be integrated together with CST. So that's why we introduce these non-parametric optimizations in the end. So there are two types of optimizations here. Yeah, the first one is we call it topology optimizations, and the second one is the shape optimizations. Okay, so let's look at the one on the left-hand side. Topology optimizations, the purpose is to find the functions. Yeah, we want to know if, let's say, this is a piece of metal where you want to cut in the end. Okay, so what they are trying to do is, you tell them, I want to cut this design space. Okay, and then I want to design my design goal. I want to achieve my design goal. So at the end of it, what they do is, they will try to cut this, whether they are going to fill it with, let's say, your metal, and the other one is, let's say, your air or dielectric. And then they will keep on running the simulations until they find the shapes that are able to achieve the design goal. Okay, so that is what they are doing over here. So this actually gives you a clue that, with this kind of designs space, yeah, we can actually we actually have a potential to reach the goal we want. Okay, and then the second one on the right hand side is called shape optimizations. So this is actually able to give you a more concrete answer. For instance, you have a shape like this, which is in 3D. Then what we want to do is, we on the surface here we have a mesh node like this, and then what they will do is they will try to adjust the positions of the nodes up and down so that we are able to find a more accurate answer to your design goal. Okay, so these are the case studies on the example we are doing. Yeah, so this is a compact monopole on the left hand side. This is dielectric resonator antenna, and this is electrical small antenna. So basically what we are doing is we are using the topology optimizations on this particular designs. You can see, this is actually the monopole with the left and right arm. Okay, and then when we try to run the non-parametric optimizations, you can see, the shape keep on changing. Yeah, the one that is red color means this is very sensitive. We need to reserve them. And then the one that the color is gone means, you can definitely remove them. Of course, at the area, you have the, the green color. Yeah, this is the places where you might need or might not need. So I think from these simulations, it actually gives you an idea. Yeah, you probably need to cut into a shape like this, and then later on, we can actually proceed with the shape optimizations to give you a better answer. Because this is actually to calculate, and at this area, they will tell you, okay, if I reserve 50% of this material, so am I going to get the desired result or not? Okay, of course, that gives you some confidence in this particular design tuning. And then on the right hand side, on the center, you have this dielectric resonator antenna is doing the same thing as well. And then this is the electrically small antenna. So perhaps this is actually, a sheet on this particular radome, and then we try to play around with these particular shapes. Yeah, this is what we are getting in the end. All right, so the next one is the shape optimizations. Here you can see this is 3D shapes. Yeah, we are trying to work on the cavity filter, horn antenna, and also the impedance matching. I think I'll try to focus on this antenna matching. For instance, you have a PCB board, and then normally, if you want to do the impedance matching, you need to calculate, what's the width of this transmission line or something, right? So when we are trying to use these shape optimizations, what we'll do is, we go to the surface over here on the outer side, and then so we tell them, you need to change this arbitrarily so that we are able to get a very good impedance matching. Let's say from, let's say 1 gigahertz up to, let's say 5 gigahertz. So the initial ones, you can see, the performance at the 1 gigahertz is bad. But after we run these shape optimizations, you can see at least we are able to achieve the desired return loss at 1 gigahertz. So I would say this is pretty good. Yeah. Otherwise, you need to, I think it's difficult to come up with a shape like this with your manual hands. Yeah. I think, this non-parametric optimizations can actually do the job. Okay. Of course, we extend this to the antenna as well. Yeah. You can see non-parametric optimizations can be supported in the unit cell simulations. For instance, you are working on the antenna array simulations. Yeah. Then the first thing you would start will be on the unit cell simulations. So from unit cell simulations, we already can get some good feeling that, a shape like this is able to give me the performance I want. Yeah, then I can proceed with the full array simulations. So that will actually increase the efficiency in the end. All right, so that's give me to the end of my presentations. So thank you so much.